Oh, it is. Okay, good. So let's start this unit 3 on trigonometry, and we'll get into this fairly quickly. So, something happened there. That's the one I wanted. Huh. I don't know. Weird. All right, so let's start trig stuff. And 5-1 starts with angles in their measure. All right. I know all of you are familiar, at least somewhat, with angle measurements. So I'll go through this pretty quickly. When we talk about an angle measurement, we mean between two rays. So we have two rays. And what we're going to be measuring is essentially the rotational measurement between one ray and the other. All right. We call this the initial. Let's capitalize that. Initial ray. And this is the terminal. Or initial side, terminal side. Whichever you like. Okay. So we're measuring essentially how much do I have to rotate that initial side to get to the terminal side. Okay. By the way, the point of rotation is called the vertex. And depending on which direction we're going, we could have positive rotation and negative rotation. Okay? Any rotation is going, let's say, in the counterclockwise. So if the rotation is counterclockwise, then we have positive angles. That's just an angle. So if the rotation is counterclockwise, we have a positive angle. If the rotation is clockwise, so we have terminal, initial, terminal. Then we have a negative angle. A lot of times, we will force our angles to be positive when we're dealing with triangles. When we're dealing with unit circle, we don't do that so much. Okay. So an angle is a measurement of rotation, right? An angle is a measurement of rotation. And usually, in a lot of applications, in triangular applications, we keep those angles positive. Not always, but the idea. Now I am going to deal with a lot of angles. And I want to introduce you to some new notation. All right. The Greek letter theta. All right. The Greek letter theta often represents the measurement of an angle. Okay, it's not the only thing that we can use to measure an angle, but so I should say for the measure of an angle. To measure an angle, but so it's not it's not an action, it's just a symbol. So the Greek letter theta, often used to measure an angle, it looks like a big O with a little bit of a line in there. Usually we try to make it a curved line. I know it doesn't look great here, but there. We're going to use that not only in this chapter, but in basically this whole unit. We're going to use theta a lot. And then when we get into unit 4, we'll use it in unit 4 as well. Okay. When we talk about polar coordinates and things like that. All right. Now, in this unit, we have to be very careful of how we're measuring an angle. There's going to be 2 different units of measurements of an angle. One is a degree measure. And the other is a radian. So we'll start with degree. Okay. Basically, you set that a full rotation all the way around so when I say a full rotation, I mean the initial side and the terminal side are the same. So we set that a full rotation, and obviously since we did that counterclockwise, that's a positive rotation. So a full rotation where your initial side is equal to the terminal side. Is 360 degrees. So we set that a full rotation is 360 degrees. And then any partial rotation is going to be a percentage or a part of that. So any lesser rotations, we say, well, what part of 360 is that? Does that make sense? So if we go a quarter of the way through a full rotation, then we get a quarter of 360, so 90. If we go half of a full rotation, then we're at 180. Okay, so a full rotation we let be 360 degrees, and all other rotations so all other angle measures are parts of that 360. So if I have a quarter of a way around a full circle, and we'll talk about this as full circle because the full rotation is a full circle, right? So you can go around a full circle. In other words, if you put a point here on the initial side and you rotate that, it's going to rotate around in a complete circle. Okay. So a quarter of that is going to be 90 degrees because that's a quarter of 360. Okay. By the way, that 90-degree angle is called a right angle. Another one that you should know is if your terminal and your initial side fall in a straight line, well, that's half of 360 degrees, so that's 180. Right, so if our terminal and our initial side form a straight line, then we have a 180-degree angle. When we get to triangles, our right angle is going to be really important. Also, any angle where we are between 0 and 90, so I'll write it this way, theta between 0 and 90 is called an acute angle. So any angle between 0 and 90, and again, this is 0 degrees and 90 degrees, if you want to spell that out, is called an acute angle. Any angle between 90 and 180 is called an obtuse angle. Now, degree measure is fine. We're going to use degree measure quite a bit in this class when we talk about triangles. Okay. However, when you get into doing calculus, if you go on to the next class, the more common measurement of an angle is going to be the radian measurement of an angle. Right? So, in calculus, we don't use degrees a lot because there's, well, the short of the story is there's links between our various trig functions when you do calculus, all right? And those links work with radian measurements, and they don't work with degree measurements. So we use radian measurements a lot when we get to calculus. So that's going to be our primary use. We're going to use degrees a lot in this class, but when we deal with trig functions, we're going to use radians a lot too. So be very careful when we're using degrees to have your calculator in degree mode, and when you're in radians, have your calculator in radian mode. Okay. So let's just switch some things. Let's talk about the radian measure of an angle. Anybody know what a full rotation, full circular rotation is? How many radians is it? Well, we set a full rotation radians to be 2 pi radians. And all other radian measures are just going to be pieces of that 2 pi. So there's nothing here. So all other radian measures are parts of the 2 pi. So if you think about it, a right angle, which was 90 degrees, has to be a quarter of 2 pi. If I take 2 pi over 4, 2 over 4 reduces to 1/2. So it's half of pi, or what we usually write that as pi over 2 radians. And 180 degrees straight line well, that's half of a full rotation. Half of 2 pi is just pi. And we could do in our acute and obtuse angles, 0 to pi over 2 and pi over 2 to pi. We generally don't talk about acute and obtuse in terms of radians, so we won't worry about that. But that's it. That's the whole thing. Radians, a full rotation is 2 pi radians. Okay. Now you might say, well, how is that better? How is that different? Here's another way to think about radians. Here's another way to define radians. And this is one of the reasons why radians are a little bit more sophisticated compared to degrees, is that radians can link to a circle, right? Let's draw a circle of radius R. A circle of radius R, whatever R is. And we're going to draw an angle whose vertex is the center of the circle. We'll call that angle theta. I didn't draw this very well. Let me redraw it. There. That one's better. So circle has radius R. Angle there is theta. Now the length of this part of the circle, the arc length here, we'll call that arc length S. The arc length between sides of the angle. Yes. So if we have this picture, then the measurement of the angle is actually just the ratio between S and R. Okay. With this picture, if you want to measure the angle theta, all you have to compute is the ratio between the S and the R, and that's how many radians it is. Now, it should make sense now why we have 2 pi radians as a full rotation. Because what's the circumference of a circle? It's 2 pi times the radius, right? So because the circumference of a circle, you don't have to write this down, it's 2 pi times radius. Circumference just is the arc length around the entire circle, right? So that's saying if theta, this goes all the way around 360 degrees, all the way around the circle, then the circumference is the arc length. And obviously, S over R is 2 pi. So that's why a full rotation is 2 pi. It's because the circumference of a circle is 2 pi times the radius. Another way to say that is if I put 2 pi times the radius here, the r's are going to cancel out and just be left with 2 pi. Or a full circle. Does that work? This length between lengths of circle compared to the ratio of the arc length compared to the length of the radius, that's why radians are really nice to deal with. Okay, is because of this length. And this linking is why it's kind of nicer to deal with radians when you do calculus stuff. So that's why we deal with radians. Now, as far as 5-1 goes, that's the setup. But a lot of 5-1 is simply, now that we know what angles are, now that we know how to deal with this, can we do some conversions? And let's convert from radians to degrees, and from degrees to radians. All right. To do this, you can use one of two options. There's the same thing. We can either use the fact that 2 pi radians is 360 degrees, or some people prefer to use the fact that 1 pi radians is 180 degrees. That makes sense? So we use one of these two. 2 pi radians equals 360 degrees, or usually pi radians equals 180 degrees. And if you know those two things, one of those two things, then you're all set. Let me show you how this is done. Let's say we have three pi over 4 radians. What is that in degrees? So we have 3 pi over 4 radians. We want to figure out how many degrees is that. Okay. Here's what we do. We take 3 pi over 4 radians, and we multiply that times a fraction. Since we want to go from radians to degrees, what we're going to do, I like to use the pi 180. Is that okay? I say I want to go 2 degrees. So I'm going to put 180 degrees on top and pi radians on bottom. When I multiply, then the radians from here are going to cancel out with the radians in the denominator. You see that? Radians on top, radians on bottom cancel out. And I'll be left with just degrees as my measurement. Okay. So that's all I have to do. Take 3 pi over 4. 3 pi over 4 times 180 divided by pi. And that's something I can just type into my calculator. If you want to do that by hand, the pi's also cancel out, so it's not that bad. But 3 pi over 4 times 180 divided by pi. I got 135. Anybody else get that? So that's 135 degrees. A lot of times I'll have this symbol rather than the word degrees. I wanted to write the word degrees there first. Is that okay? Let's go the other way. Let's say we have 54 degrees. And we want to figure out how many radians that is. Well, we're going to do the same thing. We're going to start with degrees. And we're going to multiply times a fraction. This time, in order to cancel out degrees, I'm going to put the degrees on the bottom and the radians on the top. And I use, again, a fraction that's either pi radians is 180 degrees or 2 pi radians is 360. I usually use pi 180. Okay. That's also what the book does. If you look through the book, I usually use pi 180. So pi radians is 180 degrees. The degrees are going to cancel out and it'll just be left with radians. So I take 54 times pi divided by 180. And I get about 0.9425. A lot of times, I have to round a few decimal places. Actually, this is rounding 2 decimal places right now. So it's about 0.94 radians, right? That's just the conversion. That makes sense? By the way, if things start as negatives, that's fine. If things start with radians, that's fine. If things start with degrees, that's fine. Doesn't matter. You can always just do these conversions. So I want you to try a couple of these. Let's say we want to have 2 pi over 7 radians. Convert that to degrees. That's 2 pi over 7 radians. Convert that to degrees. Let's convert also 162 degrees to radians. And let's convert negative 18 degrees into radians. And you can round your answers to a couple of decimal places, if you like. All right, any questions so far? We're good to go? All right, let's do this. 2 pi over 7 radians. So we're gonna times it. And again, I usually use the labels first. I start thinking of, okay, I need to cancel out radians. So I put radians on the bottom, degrees on the top. And then, again, if you wanted to use 2 pi is 360, just use 360 on top and then 2 pi on bottom. But if you do 360 over 2, that automatically reduces to 180 over 1. Okay, so I typically just use 180 and 1 pi. That's what I did. So I did 180 is pi radians. And then once I multiplied that, I got about 51.43. So about 51.43 degrees. 162 degrees. I'm going to multiply it. I need to cancel out the degrees and be left with radians. So I need radians on top, degrees on the bottom. Pi radians is 180 degrees. So that gives me about approximately 2.83 radians. Just looking up the homework, and it says 2 decimal places in the homework. So if you need, deal with 2 decimal places. Negative 18 degrees. Well, negative 18 degrees, just put in negative 18 degrees in the same way I did before. Radians goes on top, degrees goes on bottom. So negative 18 times pi over 180. Now, I'm gonna leave a blank here. I get about negative 0.31. So if it said round our answer to a couple of decimal places, that's fine. But I also want you to notice that if you wanted to leave pi in, you could have. What if I just ignored this pi for a second and did negative 18 over 180? Well, negative 18 over 180 is the fraction negative 110, 1/10, 1 over 10. So if I wanted an exact answer, I could have said negative 1/10 times pi, or negative pi over 10. Could follow that. And sometimes people leave the pi in so that we have an exact instead of a rounded measure for our radians. I could have done that over here as well. I could have reduced 162 over 180 and left the pi in, and whatever the reduction, I think that's 9/10, isn't it? Think about it. I think that's 9/10. But I think that's what it is, 9 pi over 10 as an exact answer. So all I'm saying is if you're willing to leave the pi in, you can get exact answers. All right? And sometimes people utilize that. Some people get exact answers rather than trying to get, rounded to 2 decimal places things. There are some, what I would call popular angles. To know, I would say the exact radians for. Now we can convert all these, but we'll just go from 0. That's easy. 0 degrees is 0 radians. 0 times anything is 0, right? Again, think of converting from degrees to radians. 0 times any fraction is 0. Another popular angle is the 30-degree mark. Let's write it down here. If I did 30 degrees, times pi over 180, and I took 30 divided by 180, I get a 6. So that's 1 pi over 6, or we just usually call it as pi over 6. I know I'm not doing the calculations, but you can figure that out. Let's step that up by 15 degrees. So let's go to 45 degrees. And if I did the same thing with 45 times pi over 180, 45 divided by 180, convert that to a fraction, you get 1/4. So you get pi over 4. 60 degrees. Well, one way you could just say it's double 30 degrees, right? You double 30 degrees, that's 2 pi over 6, which is pi over 3. And then the other popular ones that we see a lot of are 90-degree angle, which we already did earlier. So that's pi over 2 radians, because that's a quarter of the circle. And then 180 degrees, pi radians. 360 degrees is 2 pi radians. And by the way, if you wanted to do like, I don't know, 210 degrees, you could say, well, that's 30 plus 180, so I could take pi over 6 and add pi. All right? And you can do all that kind of manipulating as well. If you wanted to figure out what the angle measurement of a 15-degree angle is, you could say, well, it's pi over 4 minus pi over 6. You could do it that way. Well, if you had these ones, you could do any sum of these or difference of those. So sums and differences of those angles are good to know. There is a problem in the homework, and it might look a little strange just because of the way Moodle orients things. It'll say, for instance, 30 degrees is equal to blank pi slash blank. And what it's trying to get you to do is to know that 30 degrees is 1 pi over 6. Okay, so you write 1 pi over 6 to there. Is that okay? So these are some popular angles to know the exact radians for. Another thing I wanted to kind of highlight is angles whose initial side is the x-axis. So a lot of times, we will start with vertex of an angle. So if we're in the grid, the Cartesian coordinate plane, the rectangular grid, what we'll do is we'll start our initial side being the positive direction on the x-axis. And then we'll measure out from there. However many units we measure. By the way, from what we just did, if our terminal side is also positive direction on the x-axis, then we're at 0 degrees or 0 radians. If our terminal side goes along the y-axis, well, we know that's a quarter of the way around the grid. So the y-axis is 90 degrees or pi over 2 radians. By the way, that's about, when you do pi over 2, if pi is about 3.14, divide that by 2, you get about 1.57. So it's about 1.57 radians. Rounded to 2 decimal places. If my terminal side is the negative direction on the x-axis, then we're at 180 degrees or pi radians. And again, pi radians, pi is about 3.14. Grab one. About 3.14 radians. If my terminal side is the negative direction on the y-axis, that's 270 degrees, which is 3 pi over 2 radians. Or if you take 3 pi over 2, that's about 4.71 radians. By the way, what I've done is I've rotated this in the positive direction all the way around. And obviously, once you get back to here, that's 360 degrees or two pi radians. Right, all the way back around. So 0 degrees is the same as 360 degrees in terms of where the terminal side is. So in the sense of where is the terminal side, we get this. Now you could also go in the negative direction as well. If you go in the negative direction, what happens is that 90 degrees in the positive direction goes this way. In the negative direction, we just go this way. Does that make sense? You go from here down. And so everything's negative. So negative 90 degrees has the same terminal side as positive 270. Which negative 90 degrees is negative pi over 2 radians, which is about negative 1.57 radians, and so on and so forth, right? And if you want to go backwards, you could do it backwards as well. This would be negative 180 degrees, which is negative pi radians, which is negative 3.14 approximately. 90 degrees is negative 270. You guys know what I'm saying here? Terminal side in the negative direction, negative 270, negative 3 pi over 2, negative 4.71. So I did everything in the positive direction. You can do everything in the negative direction as well. By just taking things. I'll write all those in. The point that I'm making is that if we let our vertex be the origin, and we let our initial side be the positive direction on the x-axis, then our angles that are split 90 degrees, 180 degrees, 270 degrees actually break up the 4 quadrants of the rectangular coordinate plane. All right, you guys remember quadrants of the rectangular coordinate plane? This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. And by the way, if we land right on the x-axis or the y-axis, you're not in any quadrant. Okay. So if I were to pick an angle, and say, let's take 324 degrees. Let's convert that to radians. And determine what quadrant it's in. What we mean so if I just state what quadrant is this in, I'm saying if I start my initial side at the x-axis, what quadrant is the terminal side in? We follow that. So we can convert it in the same way we did before. 324 degrees pi radians over 180 degrees. I'll just do a rounded version this time. 324 times pi over 180. That's about 5.65. I should have done approximately. It's okay. And if I'm going to figure out what quadrant it's in, then I just go and look. Okay, 324 degrees. That's somewhere between 270 and 360, right? That's in between 270 and 360, so that's quadrant 4. So it's just that straightforward. The other thing you could have done is you could have used the radians. You could have said, well, it's 5.65 radians. And 5.65 is above 4.71, but less than 2 pi. 2 pi is about 6.28, right? So it's somewhere between 4.71 and 6.28, so it's in quadrant 4. Either way, you can use degrees or use radians. But once you kind of know the cutoff for degrees, you can always determine what quadrant things are in. So that's mostly what 5.1 is. It's about converting back and forth between degrees and radians, between those two things, and then determining quadrants. Okay. You can use some exact calculations, like 30 degrees is power of 6, that kind of stuff. Or you could use rounded versions, like 324 degrees is 5.65 radians. And then quadrants. Quadrants are broken up this way. Is that right? Now, that's just all of the angle measurements. 5.2 starts dealing with trig functions and the unit circle. Now, I'm going to do 5.2 and 5.3 kind of at the same time. Because 5.3 just does other trig functions. 5.2 just does sines and cosines, right? So we're going to kind of put them all together with unit circle. Okay. 5.2 and 5.3. So now let's get to the trig functions. Circle. 5.4 will be trig functions and right triangles. Okay. That next. So let's start with the unit circle. Unit circle is the circle with radius 1, and usually we think of it as centered at the origin. So we draw our x-axis and our y-axis. Good circling. Better circle. Better circle. Okay. Now, just like we were just doing, we're going to assume we're going to take an angle whose initial side is the positive direction on the x-axis. So we're going to create an angle. And I'll make my terminal side, just for visual purposes, ending it somewhere in the first quadrant, but it doesn't have to be this way. You can end your terminal side anywhere you want. So we're going to create a unit circle. And our angle is gonna be looking like that. By the way, let me just label this real quick. Since this is a unit circle, this point here is the point 1, 0, right? 1 unit away. And this point over here is 0, -1. And this point over here, that's it 0, -1, -1, 0, excuse me. I'm going 0, 1. Trying to think through. -1, 0, 0, -1. There's our unit circle. All radius 1 stuff. Okay. Center at the origin, and radius 1. We create an angle inside this unit circle. Now, this point here on the unit circle where the unit circle intersects my terminal side. That is going to be an ordered pair. Now, how we denote that well, there's multiple ways of denoting this. So that's kind of what the point of 5.2 is all about. All right. Let me just call it something. Let's create a function called the wrapping function. And what you're going to do is you're going to input an angle, theta. The output is going to be the point on the unit circle which intersects the terminal side of theta. Because we are in the unit circle, let me take a step back. This is kind of more theoretical than most. Unit circle, if you remember how we found degrees and we found radians, radians were linked to circles, right? So we're going to use radians here, okay? The angle will be in radians. Just for side note, when we're dealing with a wrapping function, our inputs are going to be in radians. So I want you to think through what the wrapping function would do if you input pi over 2 in it. Well, pi over 2 would be the same going along this y-axis, right? Up along the y-axis, positive. So the output should be the point 0, 1. Do you agree with that? So the output of pi over 2 would be the point 0, 1. If I put in pi, my terminal side would be along the x-axis in the negative direction, where that intersects the circle is the point -1, 0. Okay. So those are straightforward. The ones along the axis, those 4 points. So the output of 3 pi over 2 would be 0, -1. Right? 3 pi over 2's. Okay. Trying to just think real quick where I want to write this down. I don't want to. Everybody got these? Okay. Now, I want you to think about this also. In general, if we have a wrapping function, and it generates out a point, I'll call it x1, y1. Just so that we know that these are specific values, although you could just use x and y. That's fine. If you'd rather just use x and y, that's fine. It's not going to hurt. What's going to be true about that point? Well, because it's on the unit circle, this distance from the origin to the point has to be distance 1. Okay. And what's the distance formula? Well, the distance is square root of x squared plus y squared. So the distance which is the square root of x. Well, I'm just saying x squared minus y squared because x minus 0 because we're going distance to the origin. Does that make sense? That has to be 1. And the square root of 1 is 1, so you can square both sides and get 1. Does that make sense? So we have to obey that rule. X squared plus y squared equals 1. So in general, x squared plus y squared has to be 1 on any point that we have. That's going to come back to play in a very significant way in a few chapters beyond here. Not chapters, a few sections beyond here. Let me give you some other values of the wrapping function. Namely, what happens at pi over 6, that 30-degree angle? Well, pi over 6, we're here. What it turns out, you get root 3 over 2. And then 1/2. And it turns out also if you do the wrapping function with pi over 3, I'll do pi over 4 in the middle here, but I'll do pi over 3 first. Well, 30 degrees up, there's a natural symmetry with that, and 60 degrees, like down from here. And it turns out that you just reverse your x and y. And then pi over 4 is root 2 over 2 in both the x and the y value. By the way, it should kind of make sense that pi over 4, which is 45 degrees, should have the same x and y value because 45 degrees means your terminal side is the x and y equals x line. Does that make sense? So it's the y equals x line, and it's y equals x, and it has to obey this. And if you go through the calculations, that forces you to have root 2 over 2. I won't go through the calculations now, but interestingly enough. So those are some other values that are well known for the wrapping function. And you can get the decimal versions of those if you like. So how does all of this relate to trig functions? How does all of this relate to trig functions? Well, it turns out that the x and y values of the wrapping function are outputs of our sines and cosines, trig functions. Okay. So we can define sine and cosine in terms of the wrapping function. And that's what 5.1, or excuse me, not 5.1, 5.2 does. 5.2. And then 5.3 defines other trig functions in terms of the wrapping function as well. Does that make sense? So it's all the same thing. Oh shoot, you know what I should have done? I should have said something about this. So I've done wrapping function of pi over 3. There's a lot of other things you could do now that you know the wrapping function of pi over 3. We're not going to take a lot of time in this class, but let's say this is pi over 3. Okay. You could symmetrically put a point over here. And notice what would have happened to the x and y value. The y value would have stayed the same, would have stayed at √3/2, and the x value would have went -1/2. That makes sense? I think I did that right. Okay, and you could have also symmetrically put it here, and then just got negative because it's in the fourth quadrant. And you could have symmetrically put it over here and got negative in third quadrant, positive negative in the fourth quadrant. So you can play this game of symmetry with all these angles and all of their outputs. Okay, with the wrapping function if you like. I don't tend to do that manually. I tend to just say, well, let's calculate the x value and wrap and figuring out what it is to 2 decimal places, all that kind of stuff. I tend to rely a little more on calculators than I do doing the game of symmetries on the unit circle. But you absolutely can use the symmetries on the unit circle and do all that. Okay. So now let's define our trig functions. Via the unit circle. Okay. So cosine of theta is simply the x output of the wrapping function. Sine theta is simply the y output of the wrapping function. Or, in other words, if the wrapping function gives us out, I'll call it points A, comma B, then cosine of theta has to be the A, sine theta has to be the B. Now, while I have you here, I'm just going to hit up 5-3 while we're here. Okay, so this is 5-2, and then 5-2 does a lot of calculations with sine and cosine. Okay. But what I'm going to do is say also you can define the other 4 trig functions. The other 4 trig functions are secant, tangent, cosecant, and cotangent. I'm not going to write those names like spelled out. I'm just going to write the function designations to those. Does that make sense? So tangent, T-A-N-G-E-N-T of theta, but when we write it down, it's always tan theta, right? Cotangent is always C-O-T, so hopefully you all know those words. I'm sure you've dealt with or at least seen those before. So also secant is 1 over A. Cosecant is 1 over B. Tangent is B over A. Cotangent is A over B. By the way, these only exist when your denominators are not 0. So for secant, A cannot be 0. For cosecant, B cannot be 0. For tangent, A cannot be 0. For cotangent, B cannot be 0. Right? Otherwise, they would have domain errors, basically. By the way, notice that cosine and sine are A and B. So you could have just as easily said secant is actually 1 over cosine, right? And just as easily said cosecant is 1 over sine, right? As long as sine is not 0, as long as cosine is not 0. So that's why I want to do 5-2 and 5-3. So 5-2, you do that, and then you do a bunch of calculations with these two. And then 5-3, you do these, you do a bunch of calculations with those. Right? But it's all the same idea. Now, knowing this about the wrapping function allows us to do a couple of things. Now that we know, let's manually use the wrapping function. To calculate the following. All right. What if I said, let's calculate cosine of pi over 2. And let's calculate sine of pi over 2. Well, I know what the wrapping function does for pi over 2, right? For pi over 2, I'm at this point, 0, 1. So I know the wrapping function at pi over 2 gives me 0, 1. So that means the cosine of pi over 2 has to be 0. And the sine of pi over 2 has to be 1. Not too crazy, right? All right, what about pi over 6? Well, I know that the wrapping function at pi over 6 gave me root 3 over 2, comma 1/2. We saw that earlier, is all I'm saying. By the way, it's a nice exercise saying, oh yeah, if you square this plus square that, you get 1. You can check that out. Square this one, you get 3/4. To square this one, you get 1/4. Add them up, you get 1. So cosine has to be the square root of 3 over 2. And sine of pi over 6 has to be 1/2. Now, we're not going to do this a lot. We're going to do this manually. But you could, if you wanted to, get lots and lots of different angles, cosine and sine values this way. Let me take cosine of 11 pi over 6 and sine of 11 pi over 6. What you could do is you could trace 11 pi over 6 out on the unit circle and say, well, you know what? That's not very good. Here we go. That's better. 11 pi over 6. And it's there. Okay. Now, the reason I chose 11 pi over 6 is because it's actually the same thing as negative pi over 6. You guys know that? So if you take 2 pi and subtract pi over 6, 2 pi, 12 pi over 6 minus pi over 6 is 11 pi over 6. That makes sense. So that's why I chose it. I chose it for the symmetry of pi over 6, which we just did. That's what I'm trying to get at. And if you notice, we went from quadrant 1 to quadrant 4, but these 2 points will have the same x value. So the point over here will be root 3 over 2, but the y values will be different via negative. Negative 1/2. Because we're projecting across the x-axis. So that is always all to say, we can find out through some logic that if we take the wrapping function of pi over 6, 11 pi over 6, it's similar to the wrapping function of pi over 6. It has x value, root 3 over 2, and y value, negative 1/2. And you can take those 3 functions, the 3 wrapping function inputs, root 3 over 2 comma 1/2 was the wrapping function outputs for pi over 6. We dealt with pi over 4. Again, you got root 2 over 2, root 2 over 2. And then we dealt with pi over 3. You got 1/2 comma root 3 over 2. So we dealt with those 3, and you can play that symmetry game with a lot of different angles. Okay? So there's a lot of different angles, especially if the denominator is 4 or 6 or 3. So you can play the symmetry game with the 3 angles that I dealt with earlier, pi over 6, pi over 4, pi over 3. But that's not the most efficient way. So like I said, we're not going to do this way very often. What I prefer is to use our calculator, right? Our calculator has a sine and cosine function in it, embedded, and that'll allow us to do these very quickly, but it will also allow us to do calculations with sines and cosines where the angle's not nice. Where the angle I can't play this sort of project across the x-axis or project across the y-axis. Okay. Okay. So let's figure out how we would have calculated those problems or done those problems playing, well, just using our calculator rather than doing the symmetry game. So, sorry, thought I had the projector on. I did push on, but apparently the cord was out. Okay, so it's gonna take me a second. For the projector to warm up here. There we go. All right. Now, before we do anything, before we start playing with this, we have to realize we're dealing with radians here. And if we are dealing with radians, let's write this down just a little bit. I have to make sure my calculator is in radian mode. So make sure you go to mode and you're in radians. Right there. Okay. Hit enter, make sure the radians are highlighted. On some calculators, it'll just say RAD rather than radian spelled out, and DEG instead of degree. But make sure we're in radian mode. By the way, we'll change that when we get to 5.4. So now go to the home screen. Our sine and cosine button are right here. Let's do cosine of pi over 6. That's 0.866, so on and so forth. That's the decimal version of root 3 over 2. So if you ever see that 0.866, that's the decimal version of root 3 over 2, as you can see. If I wanted to calculate sine of pi over 6, sure enough, 0.5. That's obviously the decimal version of 1/2. Write that down. If I wanted to do cosine of 11 pi over 6, again, root 3 over 2. Be okay with that? And then sine of 11 pi over 6 is negative 0.5. Everybody okay? I'm just typing in using these sine cosine function keys. And obviously I'm using pi, which is just second, and then this symbol here. Is that pretty easy? Pretty straightforward, not too crazy. So using our calculator like that makes, not only is it okay to do the pi over 6, and you know, we could have done the pi over 2 as well. We did that problem, right? And we got a 0, 1 that time. We're doing that. That was a couple of. So we could have done that and saved ourselves from having to, you know, play around with the unit circle. Playing around with the unit circle is nice. It's nice to have an understanding, but as far as time-wise, using our calculator saves us a lot of time. And it also allows us to get angles that we couldn't get by symmetry. So let's use the calculator to find, let's take cosine of 2 pi over 5. That's not an angle that you can use symmetry with. And sine of 2 pi over 5. Let's do cosine of 13 pi over 7 sine 13 pi over 7. Keep writing pi first. By the way, you can find these individually too, it's not a big deal. So what are you gonna do? You're just gonna type them into a calculator and then round it a couple decimal places. I want you to go ahead and do that on your own and then do the same thing. I want you to see what happens when you do cosine of negative 13 pi over 7. Write pi first. And when you do sine of negative 13 pi over 7. It's rounded a couple of decimal places. All right, so 2 pi over 5, when I type in cosine of 2 pi over 5, I get about 0.31. If I put in sine of 2 pi over 5, I get about 0.95. Right? By the way, if you squared those two numbers and added them up, you'd get 1. Or if you did the rounded version, you'd get really close to 1, right? If you did the exact version, you'd get exactly 1. Because that pair, the x value squared plus the y value squared, has to be add up to be 1. Couple other things. Let's do 13 pi over 7. 13 pi over 7. Let's say that with cosine. Cosine of 13 pi over 7 is about 0.90. Sine of 13 pi over 7 is about negative 0.43. Again, if you squared those and added them up, the exact values, you get exactly 1. If you do the rounded values, you get pretty close to 1. Oh, one thing on the homework, don't expect, these are, when I ask you for cosine and sine calculations, they don't always come in pairs, okay? So I'm not always gonna ask you cosine of this number, sine of the same number. Sometimes I'll ask cosine of 2 pi over 5, and then let's do cosine of 13 pi over 7. And let's calculate sine of 18 pi over 15, you know, something like that. So they don't always, in homework, it's all different numbers. But I do like to have them in pairs because these are coming from the rapid function, right? At least on the board, I like to deal with them in pairs. Homework's not so much. All right. Now you'll notice that when you put cosine of the negative of 13 pi over 7, you get 0.90, the same number once again. But when you did sine of negative 13 pi over 7, you actually got a positive 0.43, roughly. Should have. And I want to tell you why that always exists. If I take these two angles, 11 pi over 6 is actually the same thing, same ending point here as negative pi over 6. Everybody follow that? So whatever angle I have, the negative of that angle is actually projected across the x-axis. So there's some symmetry here with the x-axis and the positive angle versus the negative angle. And that's what you're seeing here. 13 pi over 7 is somewhere down here. I don't know exactly. Let's think. Yeah, it's pretty close to this, I guess. Somewhere like this. If I project it across the x-axis, I get this point here. So they're both going to have the same x value, but the y values are going to be swapped. And so when you put in cosine of an angle and cosine of negative that angle, you get the same thing. When you put in sine of the angle and sine of negative the angle, you get the opposite number. Does that make sense? A little bit. Also notice that if you think about where 2 pi over 5 is, without knowing anything else except where the cosine and sine are, these are both positive numbers, right? Let's pretend I didn't know this was 2 pi over 5. Let's say I just said, here's my angle. They both give me out positive values. What quadrant does my angle have to be in? It has to be in 1, quadrant 1, because that's the only place we're going to get points where we have a positive for the cosine and a positive for the sine. Okay. And the same thing is true over here. If I said, well, I know my cosine of the angle is positive, and cosine's going to be positive. If sine is going to be negative, well, that means positive x value, negative y value. I know that's going to be in quadrant 4, whatever the angle that is. That makes sense? So you can determine the quadrant the point is in based on just whether the outputs of cosine, well, determine what quadrant the angle has terminal side in, just based on the outputs of sines and cosines. You can also now use our calculator to find a wrapping function of some random angle, right? 3 pi over I want to calculate the wrapping function where my input is 3 pi over 11, or my wrapping function let's say 8 pi over 5. Well, I can use my calculator to find those. I know that wrapping function has cosine of the angle as its x value, sine of that angle as its y value. I can simply plug that into my calculator. I got about 0.65 for my cosine. And about 0.76 when I plugged in the sine. Okay. Cosine 8 pi over 5, comma sine 8 pi over 5. Whatever that point gives me. I got about 0.31 as my x value and about negative 0.95 as my y value. There. Is that okay? By the way, 3 pi over 11, we could have earlier figured out that had to be in quadrant 1 because that's between 0 and pi over 2. But now, looking at the wrapping function, it's positive, so I also know that it's quadrant 1, right? I can figure it out that way too. 8 pi over 5, without even knowing what the angle, it's positive in the x direction, negative in the y direction. So it's down here in quadrant 4. Somewhere. Actually, probably somewhere close to that, I guess. Somewhere in there. But I know it's quadrant 4. Remember, if you land at 1, 0, if you land at 0, 1, your terminal side, that's not in any quadrant. If it lands on the x-axis or on the y-axis, not in any quadrant. So pi over 2, terminal side is not in any quadrant. It's on the axis. Before I move on, to doing some calculations with the other trig functions, I do want to make some observations about sines and cosines. I was kind of making the observation earlier, about the positive versus negative inputs. Cosines are not affected by that, sines are negated. But even more generally speaking, cosine of an angle has to be the x value on a unit circle, right? The smallest x value it can possibly be, the left hand most x value it could be is -1. The right hand most x value it could be is +1. So the observation that I want to point out is that cosine of an angle is always going to be somewhere, I wrote that wrong, between -1 and positive. And the same thing goes for sine. Sine, the smallest y value it can take on, the unit circle can take on. So the smallest y value on the unit circle is a -1. The largest y value on the unit circle is a +1. So also sine of an angle is bounded by -1 to positive. All right. There's lots of other observations I was kind of making as we're kind of going through that I'm going to come back to. All right. But those are more trig identities that we're going to see in later sections. So a lot of the stuff we'll see in later sections. Trig identities. Now let's say we want to calculate with some other trig functions. So let's say I wanted to take a secant of 2 pi over 5. I wrote those identities earlier. Remember, secant is 1 over a, where a was cosine. I'll spare the thetas of thetas. So if I want to calculate secant of 2 pi over 5, what I do is I simply type into my calculator 1 divided by cosine of 2 pi over 5. and I get 3.24 roughly. Now, if I wanted to do tangent of 2 pi over 5, remember we said tangent is well, it was b over a on the thing, right? But the b was sine. And the a was cosine. Now, I want to kind of distinguish between these two for a second. If I take sine of 2 pi over 5 and divide by cosine of 2 pi over 5, I end up with 3.08, roughly. We okay with that? By the way, notice that just because sine and cosine are between -1 and 1, when you're dividing by decimal, you can be anything, right? So secant is not going to be between -1 and 1 all the time. Tangent is not going to all the time be between -1 and 1. They can be higher than that. Tangent can also be between like -1 and 1 if it wants to be sometimes. Sometimes the denominator is bigger, sometimes the numerator is bigger. Secant is always going to be 1 or more, or -1 or less. Does that make sense? Yeah. Got to be the reciprocal of cosine. And if you're reciprocal of cosine, then you're outside of 1 in absolute value. Now, I wanted to point sort of a distinction between these two. All right? Let's see if I can get my, yeah. On the calculator, when you type things in, I did the long way to do tangent. Sine of this divided by cosine of this, okay? Obviously, there's a short way to do tangent as well, and that's just do the TAN function, okay? Tangent of 2 pi over 5, you can simply type it in and got the same answer. Okay. So with the A, B things that I had earlier, you could have calculated. You could have also just typed in tangent. So there is a tangent function on the calculator. There's not a really easy secant function. All right. So if you're trying to do secant, you actually have to do the division by cosine, or at least that's the easiest way to do it. So if you're looking for secant, doing 1 over cosine is probably your best bet. When you're doing tangent, doing just tangent is probably your best bet. Okay. By the way, similar with cosecant. Let's say I wanted to do cosecant of 7 pi over 8. I do 1 divided by sine of 7 pi over 8. I'm just picking out 7 pi over 8. Nothing significant about that. So that's cosecant. Now, cotangent would be cosine over sine, right? And you could do cosine of 7 pi over 8 divided by sine of 7 pi over 8. But you know how to do it another way? How do you do cotangent? Different way? Well, it turns out if sine over cosine is tangent, the reciprocal is cotangent, right? So if I did cosine 7 pi over 8 divided by sine 7 pi over 8, the easier way to do that is to realize that's the reciprocal of tangent. So just do 1 over tangent. Okay. So that's the shorter way of typing that in. So if you're trying to do calculations with sines and cosines, and you're using sines, cosines, and tangents on your calculator, we can know that. And that's what I was going to get into. So let me just write this out. When using calculator, if I want to find the secant of theta, what I usually do is I just do 1 over cosine of theta. If I'm doing the cosecant of theta, that is 1 over sine of theta. Tangent, I just use tangent usually, but you could have also done sine over cosine. When you're doing cotangent of theta, you could have done cosine over sine, but you could have also done 1 divided by tangent. All of these work so long as we don't have 0 in the denominator. Okay. So all of these work. Denominator. So you always have to say, this is true, so long as denominator is not 0. Denominator is not 0. If the cosine is 0, secant's not defined here. If cosine is 0, tangent's not defined. If sine is 0, cotangent's not defined. Sine is 0, cosecant's not defined. So that's all. Any questions about this? So just use your calculator in this, and you can find any other trig function. We're almost done with 5.3. We'll probably start a little bit of 5.4. Well, we'll probably do maybe a little bit more calculations of 5.3 just as a reminder of these. But it's pretty easy calculator work from here on. in the rest of 5-3. Okay? And then we'll start on 5-4 next time. All right? I'll see you next time.